and welcome to the Geometric channel. Today's lesson is all about triangles. We'll look at a bunch of different ways to classify triangles and explain why the angles in a triangle always add up to 180 degrees. If you'd like to take notes, click on the link down in the description and you'll find a guided notes worksheet that you can print off and follow along with me. So let's start by quickly defining some of the different ways that we can classify triangles. Triangles can be classified by their angles and by their sides. So these classifications, some of these words you probably heard before, but maybe not in the context of a triangle. So we'll just start over here with, let me try again, I can make it better. What we call an acute triangle. Now an acute triangle is simply a triangle that has all acute angles. If you remember, acute just means an angle that is less than 90 degrees. So if all three angles in the triangle are less than 90 degrees, that is what we call an acute triangle. Next triangle, you're probably familiar with this one. If you have a triangle with a right angle, an angle of 90 degrees, this is what we call a right triangle. Okay, so again, notice we're just classifying these triangles based on the angles that are inside of them. Third one here. This is what we call an obtuse triangle. You can see that one of the angles in the triangle is obtuse, or more than 90 degrees. So we call this an obtuse triangle. And then finally, if you have a triangle where all three angles are congruent, or in other words, all the angles are equal, that's what we call an equiangular. An equiangular triangle. Okay, so all angles equal, that is equiangular. Okay, so that's 4 ways you can classify triangles based on their angles. Let's talk about how to classify them based on their sides. So the first one, similar to the equiangular triangle, if all three sides are congruent, this is what we call an equilateral triangle. Right out of room here. Right here. Okay, it's called equilateral. All three sides the same. Next is if two sides are the same. Okay, so two congruent sides and then one side that is a different length. That's what we call an isosceles triangle. Isosceles. And then finally, if none of the sides are the same length, all three sides are different, we call that a scalene triangle. Okay, so each time you classify a triangle, you will be able to take one classification from the angle section, one classification from the sides. It could be, for example, a right isosceles triangle, or it could be an obtuse scalene triangle. Now I want to go back up here for a second. I'm going to think about these two, obtuse and equiangular. An equiangular triangle, again, all three angles are the same. There is a specific angle measure that all three angles will have to be equiangular. And that is, all three angles would have to be 60 degrees. Another thing that we know, that if it's an obtuse triangle, could there be more than one obtuse angle in that triangle? Okay, if you think about what a triangle looks like, the three sides being closed, could you make a triangle with two obtuse angles? Well, if you started one here and then you maybe made another one, well, we're not going to make a triangle in that case. Okay, so if you think about what a triangle looks like and how it's created, we're bound by the total sum of the degrees in that triangle. Okay, and it is true that a triangle will always add up to 180 degrees. So think if I had an obtuse angle that's more than 90, and I had a second obtuse angle that's more than 90, I already know that 90 and 90 is 180. I can't have more than 180 degrees. Now, why is that? How can we prove that a triangle is always 180 degrees? Let's do that. So this fact that a triangle, the angle measures in a triangle always adds up to 180, this is called the Triangle Angle Sum Theorem. There's a couple different ways to prove that, but I think the easiest way, especially if you've talked about parallel lines and transversals, is to look at a situation like this. So let's say we have a couple of parallel lines. And in the interior of those parallel lines, let's create a triangle. So a triangle, let's say I have our three endpoints, three vertices here. And we've created a triangle to where one of the sides of the triangle is one of those parallel lines. So this side here at the bottom, and then we've got the side at the top that's parallel that goes through that third vertex at the top. Okay, so what I want to do is I want to look at the angles that we've created in this situation. So I've got angles here, call that 1, 2, and 3. And then we've got down here 4, 5, 6, and 7. Okay, so the three angles that are inside the triangle, so the interior angles of the triangle, we've got angle 2, angle 5, and angle 6. Okay, and we say, or our hypothesis here is that those three angles are going to have to add up to 180. So how do I know that? Well, knowing what we know about parallel lines and transversals that cut through parallel lines, we have some angle pairs that we know certain facts about. Now, if you haven't talked about things like alternate interior angles and same-side interior angles, if that doesn't ring a bell, I want to go check out that video right there. It's going to explain things a little bit better. But if you already know about those kind of things, this should make a lot of sense. So one thing that we know that in parallel lines cut by transversals, we've kind of got two transversals here. I'm going to start with this transversal on the left, so this side of the triangle. I want to look at angle 1 and angle 5. So if we were to classify those two angles as one of those angle pair types that we just talked about, what would those two be? You should see that those are alternate interior angles. Okay, so angle 1 and angle 5 are alternate interior. Angle 1 and angle 5 are alternate interior angles. Okay, and if I look at the other side, this other transversal over here on the right, I know that angle 3 and angle 6, same idea. Those are also alternate interior angles. Okay, angle 3 and angle 6 are alternate interior as well. Okay, and if you remember, the property about alternate interior angles is that as long as the lines are parallel, alternate interior angles are always congruent. I already marked them congruent, you can see them there, but that is a theorem about alternate interior angles. They're always the same. Okay, so if I know that angle 1 and angle 5 are the same, they're alternate interior, just like angle 3 and angle 6 are the same, those are alternate interior. Now I can kind of piece together a little equation that can help me get to all three angles inside the triangle being 180. And this is what it looks like. Looking up here at angles 1, 2, and 3, I know that a straight line, looking at this line up here, a straight line, if I've got angles that are all kind of back to back on a straight line, I'm talking about these three angles right there, a straight line is 180 degrees. Okay, we know that a straight angle is 180 degrees. So I know that angle 1, angle 2, and angle 3 together, all three, have to make 180 degrees. Okay, but at this point, all I really have to do is some simple substitution to get to where angle 2, 5, and 6 would have to be 180 as well. Because I know that angle 1 is the same as angle 5, they're alternate interior. So if 1 and 5 are the same, I can substitute angle 1 with angle 5. So substituting angle 1 with angle 5, plus angle 2, I'm going to keep that one, plus angle 3, but again, I know that angle 3 and angle 6 are the same. I can substitute angle 3 with angle 6. So I'll plug that in right there. And you can see that I've got angle 5, 2, and 6, which are the three angles inside that triangle, all equal to 180. Okay, so I can do this with any triangle. I can draw a pair of parallel lines that bound that triangle, and I can use those parallel lines to get those different angle types to where I can get those three angles to add up to 180 degrees. Okay, so this right here, this is what we call the Triangle Angle Sum Theorem. Every triangle, the three angles will always add up to 180 degrees. Now, there's a theorem that kind of follows this fact. that's kind of helpful in some circumstances. And it's called the Triangle Exterior Angle Theorem. Okay, the Triangle Exterior Angle Theorem has to do with the exterior angles of a triangle. If you don't know what an exterior angle is, that just means if I take one of the interior angles and extend it out in one direction, interior angles would be bound inside the triangle, exterior angles would be like this angle right here that's sitting outside the triangle. So I'll just call that angle 1 for a minute. So angle 1 is what we call an exterior angle. Interior angles would be like these two. So like angle 2 and 3, those are interior angles. So if I know that a triangle adds up to 180 degrees, that means that the exterior angle of a triangle, okay, so one of the exterior angles will always be equal to the sum of the two non-adjacent interior angles of the triangle. Okay, say that again real quick. The exterior angle at one vertex of a triangle will be equal to the sum of the two non-adjacent, meaning not touching, so we're not talking about this guy right there, the two non-adjacent interior angles. Now, why is that? Again, that's the fact that if a triangle adds up to 180 and two angles next to each other on a straight line add up to 180, we can kind of pair some things together, maybe even skip a couple steps if we're trying to find missing angles here. Okay, so just to put some numbers in here to make it make a little bit more sense, let's say that angle 2 was 70 degrees and angle 3 was 60 degrees, and I wanted to find the measure of angle 1. Okay, one way to do this would be kind of like the long way, is that if a triangle adds up to 180, I can add the two angles that I already know and subtract that from 180, subtract that sum. So let's start there. If I've got 180 degrees total in the triangle, I've got 60 and 70, which if you add 60 and 70, you get 130 degrees. And I subtract those to get this third angle here. 180 minus 130 is going to be 50 degrees. So I would know that this angle here is 50 degrees. Okay. And then if I wanted to get angle 1, I've got this linear pair, these two angles here right next to each other on a straight line. We know those are always supplementary. So I could take 180 minus the 50 degrees to get to angle 1, which ends up being 130. But where did we see 130? Right here, which was the sum of those two non-adjacent interior angles, 60 and 70. So we can kind of skip this extra step of subtracting to get from 2 and 3 to get this angle, and then subtracting from 180 to get this angle. We can kind of do this little shortcut. If I just add 60 and 70, that's going to get me that angle 1, which is 130. Okay, so this is the exterior angles, or the triangle exterior angle theorem. Okay, add the two non-adjacent interior angles to get the measure of the exterior. Okay, so let's kind of tile this together. Let's do some real examples so you can see how we use this thing. So I'll do another exterior one real quick, show you a different way you can use it. So let's say we're missing this angle here inside the triangle. We're given a couple of angles. None of this is drawn to scale, so just go by the numbers here. Okay, so we've got an interior angle missing, we've got one interior angle that we know, and we've got the exterior angle. Okay, so again, we know that the triangle exterior angles theorem says that this exterior angle is equal to the sum of those two interior angles. So we can use that kind of in reverse to get back to the angle that's inside the triangle. How do we do that? Well, if these two added together get the exterior, I can just take the exterior and subtract the one interior that we have to get the other interior that's missing. So all I'm doing here is taking 84 minus 51, and that's it. That's going to get me my angle measure here. Okay, so this angle right here, this x would be 33 degrees. Just to go back and check, 51 plus 33 is going to get you that 84. So it's a nice little shortcut not to have to deal with this angle in here. If I don't need to, I can go straight to that interior. Okay, next one. So let's take a look at kind of a situation where you have maybe multiple triangles in one diagram. Okay, Okay, so really I have 3 triangles here. I've got the entire triangle, the big one, then I've cut down here to get 2 triangles, one on the left, one on the right. Give you a couple numbers. Let's say that's 62. That's a 56 right there. And we'll go 25 here. And we're missing, we'll call it X, Y, and Z. Okay, so 3 angles that are missing, 3 angles that we know. Okay, again, the nice thing about triangles is that every triangle, regardless of its shape or size, every triangle is going to add up to 180 degrees. So I've got 3 triangles here that I can work with to get that. We also have some exterior angles. Okay, so like this triangle right here, this is extended side. Angle Y would be an exterior angle, so we can use that here in a second. But let's start with a triangle that we know 2 out of the 3 angles, and that would be this triangle right here on the right. Okay, so if I know 2 out of the 3 angles, I'm just going to subtract the 2 angles that we know from 180 to get that third missing angle. So I've got 180 minus the sum of 56 and 62. If you add those together, you're going to get 118. So if I subtract 118 from 180, it's going to get me angle Z. And 118 subtracted from 180, that's going to be 62. So I got angle Z here is 62. Okay, so angle Z is 62. Okay, the next thing, again, since I have a triangle here, this is an extension to where this angle Y is an exterior angle. The 2 non-adjacent interior angles are 56 and 62. That exterior angles theorem says that that angle is equal to the sum of those 2 angles. And I already did that. It's right here. So angle Y is going to have to be 118 degrees. Okay, if I wanted to, again, I could just subtract 62 from 180, that straight line, that linear pair, but I already have that shortcut. I've already done that work, so let's not do more than I have to. Okay, the last angle that we have now is angle X over there on the far left. So now that I have the 2 angles inside this triangle here on the left, I can use these 3 angles, since those 3 have to be 180. I could also use the entire triangle here as a whole. I can go 62, I can add those together, and then I can get angle X by doing the same thing. Let's just use the 3 angles here on the left. So I've got 118 plus 25. If you add those together, 118 and 25, that is 143. So if I take 180, subtract that 143, it's going to get me 37. So angle X over there, 37 degrees. Okay, so again, if you know 2 angles of the triangle, subtract those from 180, that's going to get you the third. Okay, so there we go. X is 37, Y is 118, Z is 62. Now, while we're here, let's classify some of these triangles in some of the ways that we talked about before. First of all here, if I look at the triangle on the right, okay, the triangle on the right, notice I've got 2 62-degree angles. I know we didn't really talk about this, but if you have 2 base angles, 2 angles congruent, that also means that your 2 sides are going to be congruent. And if 2 sides are congruent, we call that an isosceles triangle. So that right there is going to be an isosceles triangle. Also notice that all 3 angles are less than 90 degrees, so that would be an acute isosceles triangle. Triangle over here on the left, notice we have 1 obtuse angle, so we can call that an obtuse triangle. And since all the angles of this are different, all the angles are different measures, that means all the sides are going to be different lengths, so we can call that an obtuse scalene triangle. Okay, let's do one more example here. In this last example, we're going to do a little algebra here. Okay, so let's say in this triangle, we've got, as always, 3 angle measures. We're going to call that angle 3x degrees. This is going to be a 35-degree angle. And then up here in the corner, we're going to call this x minus 15 degrees. Okay, so you might see these in your problems where they just throw some expressions in for some of the angles instead of just whole numbers. We don't change the way we do anything, it's just going to be a little different. We have to set up some equations to solve. Okay, so by meaning we're not going to do anything different, I still know that all 3 angles have to add up to 180. This time it's just going to look like an equation instead of just doing adding and subtracting whole numbers. So if I add up all three of these angles together, I can set that equal to 180 degrees. And since I've just got one variable, I've just got x's, this won't take too long. So if I add up all three together, I've got 3x plus the x minus 15. I'm going to kind of put that in parentheses here, and then plus 35. All three of those angles have to equal 180 degrees. Okay, so if I'm solving this equation, the first thing I want to do is combine like terms and simplify this a bit. Because I'm just adding this term to the other two, I don't really need the parentheses, but sometimes, especially if you have maybe some negatives, or if you're multiplying or dividing, anything like that, it's always good to put those expressions in parentheses. In this case, I can drop them. So let's go ahead and add our like terms together. I've got 3x plus x, which is really just 1x. That gets us 4x. I've got this minus 15 plus 35. 35 minus 15 can be combined to a plus 20. And then equals 180. If I isolate my variable, I want to get that variable term by itself. I'm going to subtract the 20 from both sides. I've got 4x equals 180 minus 20 is 160. And then finally we can divide both sides by 4 to get that x by itself. And 160 divided by 4 is 40. Okay, so I've got x equals 40. And let's say that my task here was to figure out what the measure of each of these angles in the triangle were. So if I've got x is 40, I can come up here and I can plug in 40 into my x. So I already got that angle is 35 degrees. If I have x is 40, 3 times 40, which is 120 degrees. And then finally, x being 40, 40 minus 15, I know that this angle right here would be 25 degrees. So we got a 25 degree angle, 120 degree angle, and a 35 degree angle. And this once again would be an obtuse scalene triangle. All right, so that's the deal on the Triangle Angle Sum Theorem and all the different ways you can classify triangles. Give this video a thumbs up if it was helpful for you, and subscribe to the Geomastic channel for more videos just like this one. Thanks a lot for watching. We'll see you next time.